Materials Project Number 5 by Josh Webb, Owen Champion, and Patrick Nemina. Okay, so here we have topic 1. Topic 1, we're going to be talking about conductors, insulators, and semiconductors. So for this, we're going to try to explain this for Grandpa Joe. So Grandpa Joe doesn't quite understand how these work. So a conductor is a material that lets electricity flow very easily. An insulator completely stops the electricity from going through, and a semiconductor is the middle, so it can either allow electricity to flow or it can either stop the flow of electricity. So if we take a look at both of our pictures over here, we see that there's an open door and there's a closed door. Think of the open door as a conductor. When the door is open, then you can walk through, you can walk in and out and flow very easily. There isn't any stopping, there isn't anything getting in your way. The door's wide open. You don't even have to open the handle. You don't have to do anything. It's just wide open. It can flow easily. Anybody can come through in and out. Think now, look at the closed door. The closed door is your insulator. Your closed door stops you from going anywhere. So when the door is closed, you can't enter, you can't go in, you can't go out, and the door's locked. You don't have a key, you don't have anything. The door is just locked and closed. There's no way to get in, there's no way to get out. Now, when we think of a semiconductor, think of the semiconductor as a lock, as you can see down here. So, for your semiconductor, if you put a lock on a door, then the only way you can get in is if you have a key for it. So if you have the key, you can open it, and then you can allow electricity to flow in and out. But if you don't want electricity to flow, you can put the lock on the door, and you can't open it, you can't get in or out. So that's what a semiconductor is. A semiconductor, depending on how we want it to behave, we can either allow it to flow electricity, or we can either stop the flow of electricity in the semiconductor.
Topic 2. Directions. Explain to a first-year ME student that has not yet taken ESC 220 the three types of primary bonds, van der Waals interactions, hydrogen bonds, energy bands, and band gap theory. Primary bonds. There are three kinds of primary bonds: ionic bonds, covalent bonds, and metallic bonds. Each bond has its own strengths and weaknesses. Ionic bonds. An ionic bond is formed when one atom donates an electron to another atom. This is typically done between metals and nonmetals on the periodic table. They form strong, brittle, high melting point materials, typically ceramics. Covalent bonds. A covalent bond is formed when atoms share electrons to form full outer electron shells. These bonds often occur when two nonmetal atoms bond, such as a bunch of carbon atoms coming together to form diamond. They make very hard, brittle materials. Metallic bonds. Metallic bonds are unique to other types of bonding, as the electrons that are used to make the bonds do not actually bond with one singular atom, but rather the electrons float around in a sea and are transferred from atom to atom. Van der Waals interactions. Van der Waals interactions are a faint static cling that occurs between molecules. These are caused by the movement of electrons creating tiny temporary charges. These are between atoms but do not create a new material. These forces hold the material together on a larger scale. One example would be how the layers of graphite are held together. Hydrogen bonding. Hydrogen bonding is similar to van der Waals interactions. It is stronger than van der Waals interactions but weaker than primary bonds. This occurs when hydrogen is attracted to an extremely electronegative atom nearby, such as oxygen or nitrogen. Examples of this would be why water has such a high boiling point. The hydrogen bonding holds the water molecules together longer, preventing them from entering the gaseous state of matter until a higher temperature is reached. Energy bands and the band gap theory. In energy bands, there are two types of bands: valence bands conduction bands. Valence bands are where the electrons normally sit, and conduction bands are bands where the electrons are free to move about the material. Band gap theory is that conductors have no gap between these bands, allowing for free electron travel between the bands. Semiconductors have small band gaps where the electron can jump when they get a little bit of energy through things such as heat or light. Insulators have extremely large band gaps and do not allow for electrons to move freely between them, and therefore do not transfer electric charge very well or even at all. Equation for resistance. R equals rho times L over A, where R equals resistance, rho equals density, L equals the length of the wire, and A equals the cross-sectional area of the wire. The larger the area, the smaller the resistance. This is proved in the equation for resistors in parallel. The resistors in parallel create an equation of 1 over R equals 1 over R1 plus 1 over R2, and so on. In series, however, the longer the chain of resistors are, the more resistance there is. The equation is R equals R1 plus R2, and so on. Therefore, the longer the resistor, the more resistance.
Hey, this is Owen, and I'll be going over topic 3, part 1 on this slide, which is the electricity in semiconductors. So in a semiconductor, there are conduction electrons, which are electrons that are free to move and carry current. Holes are the missing electrons, and they act like positive charges. And mobility is measured by how easily electrons or holes move when you add an electric field, which would be a voltage. An intrinsic semiconductor is made out of pure material. So like on the bottom left, the image shows that there's nothing else but silicone in it. And an extrinsic semiconductor is a dope material. So it has an example in the middle. Phosphorus is in the middle of the silicone molecules. So you can think of electricity in semiconductors as like a theater. And in the theater, people are the electrons and empty seats are holes. When the electric field comes in, it gets everybody moving, and the moving people make the holes move around too. The missing seats are moving around as people are moving around, switching seats like playing musical chairs. And if the theater is intrinsic, there aren't that many people, and they have a lot of holes. And if it's extrinsic, we just let a boatload of people in and fill the holes, and it moves more seats. So this is what's going on at the molecular level of the semiconductors, which would be metalloids. On this slide, I'll be going over part 2 of topic 3, which is light emissions and how LEDs work. So we're going to compare gallium phosphide with gallium arsenide. When gallium phosphide has a large band gap, so it emits a green light. And gallium arsenide has a smaller band gap, and it emits an infrared light. So to explain how this works, when an electron drops from a higher energy state to a lower state, it recombines with a hole and it releases a light. So it comes down from up here down to the hole, and the light's color depends on the energy of that drop. So the energy of a drop from all the way out here to here will be higher than an energy drop from here to here. And the higher the energy drop, the bluer the light, and the smaller the drop, the redder the light. So if it has a big drop, it's on this side of the table, and if it has a small drop, it's on this side of the table. And different elements have different band gaps, so some elements might have a larger drop than others.
Okay, so for topic 4, you might need to grab a notebook so you can follow along or write this down with me because it is pretty long and lengthy. So, and I'm not going to be able to write all of the information or write out everything on 2 here, so I'll do my best. But for this one, it's a multitude of questions. Basically, we have to find the electron mobility, the hole mobility, so just right here, so you guys can see. And then we're going to have to find the concentration of free electrons. And then we have to find the electrical conductivity. So we'll pause at these 3 questions and then we'll continue if we need to. Not when we need to, but moving forward, we'll look at those. But for now, let's write down our electrical conductivity formula. So electrical conductivity equals our elementary charge, which is that, multiplied by our carrier concentration, multiplied by our electron mobility, just right here, times our hole mobility. Sorry, that's really bad. Let's cross that out. This, and then, so that's our formula. Looks a little sloppy, but I don't think do I have an eraser? Oh, yes I do. Let me go back and fix this for you guys. So that's our formula right there. So keep up. The mobilities of electrons and the hole mobility, that we're going to just be typical literature values. So for our electron mobility, we have 1,350. And for our hole mobility, we have 480. Now, as we write it down, fill it into the equation. So we're going to fill that in right there. For our carrier concentration, we're going to use the empirical formula, which it's a long process and step, which I don't think we have time for, but that gave us the values 9.69 times 10 to the 9th. And then our elementary charge is a constant. So the elementary charge stays the same for every equation. So if you were to get a different material, or let it be iron or something else, it'll still be the same elementary charge, which is 1.602 times 10 to the negative 19th. So when we plug all of that in to our formula, that gives us 2.84 times 10 to the negative 4th. So our elementary charge would be 2.84 times 10 to the negative 4th. Next, if we have a 1 millimeter squared wide and 1 centimeter long silicone resistor, what is the resistance along the length? So first, our resistance formula is resistance equals 1 over your electrical conductivity. So if you plug it into your calculator, that gives you 3.52 times 10 to the 3rd. Now, finally, to find the resistance along the length, our formula is going to be R equals resistivity times length over here. So for this, it's going to be, well, first our L is 0.1 and our A is going to be 1 times 10 to the negative 6, which is 0.111. I don't know how many zeros there are, but if you plug all those in, that gives you 35.2. 35.2. Now, what if the temperature is increased to 700K? Now let's move into that. If the temperature were to be increased to 700K, then for this one, I don't think I have the room to write it out, but if you go through our example that we just did, first you would have to find the electron mobility and hole mobility, which is typical literature value. So you can, search that up, and it should give you that answer. And if you wanted to find the concentration of free electrons or the carrier concentration, you'd do the same thing that we did earlier, which is the empirical formula. And then after that, we'd use the same formula that we used up here and plug in our values that we got. And if you do it correctly and properly, then you should have gotten for the electrical conductivity, you should have gotten 99. And for resistivity, you should get 101. Topic 4, question 2. So for this one, it's going to be a little bit different because first we are looking at a question and it says that silicon is doped with 2e19 centimeter cubed boron atoms, and we need to find N and P at 300K. And we also need to find the electrical conductivity. So this question is the exact same as the last question. It's just that this time we're going to need to figure out N and P. And when we figure out N and P, then for the rest of the questions, we're just going to proceed accordingly or proceed to the same way we did with the first question. So it's not going to be too much writing or examples. Once we get our numbers, then it's just a matter of plugging in. So our new equation for this one is going to be electrical conductivity equals N electron mobility plus P times the hole mobility. For my last slide, I kept saying multiplication, but it's actually addition. So for the last slide, if you were getting the wrong answer and you were plugging it in and it was giving you the wrong number, it's because it's supposed to be plus, not multiplication. You're supposed to add your electron mobility and your hole mobility. So that is a mistake on my part, but my answers were correct. I just wrote it down and said it as multiplication, but I was actually adding them. I didn't catch myself, but now that I caught myself, I fixed it. So for this one, our P is actually going to equal 2e19, or 2 times 10 to the 19th. And our N is going to equal our carrier concentration squared, which we had on the last problem, over our P. So N is going to equal 4.69. So that's going to be our N. So for this one, I don't want to take too long and write it all down, but it's the same process as the last question. As I said, you plug in, and so what you should be getting is that the electrical conductivity for 300K is 1.54 times 10 to the fifth. For um for your resistivity, it should be 6.5 times 10 to the negative 6. And for your resistivity along the length, it should be 0.0650. And at 700K, it should be your electrical conductivity should be 2.38 times 10 to the fourth, and your resistivity along the length should be 0.42. So yeah.